Hey everybody, welcome. I think you gotta put the headphones on and hopefully you can hear me amid this noise and other people who join will catch on. But welcome to, I suppose, the first afternoon session in this very loud and noisy area. So hopefully, hopefully this is good and everyone's awake. All right, so my talk is called Beyond the Privacy Utility Trade-Off. My name is Lipika Ramaswamy. I am an applied scientist at NVIDIA, and I work on synthetic data and the intersection of that with privacy-preserving machine learning. And then just kind of like everything in between, because now synthetic data is almost as common as LLMs are, slash almost every foundation model has synthetic data in its training mix. So super common, but we're going to talk about differential privacy in data synthesis. And really what I mean by this is text and tabular data. I'm not going to cover images today, but a lot of what I'm saying is broadly applicable to image, video, audio data as well. So it's just roughly like the algorithms and the tooling that we use to generate differentially private synthetic data. All right, so this talk is collaborative work with my colleagues, Andre Manuel and Amy Steyer. We're going to cover several things. First of all, like basics of privacy and synthetic data, what it is, why privacy matters, what is differential privacy. I don't know how many folks here are familiar with it. Maybe like show of hands, and then I'll know who's. Okay, perfect. So folks kind of know what differential privacy is. We'll go into it in some detail, but I will not be writing proofs here, no theorem proving, just very simple, easy to understand explanations. And then we'll cover some tooling via Gretel Safe Synthetics to generate DP synthetic data, the privacy utility trade-off, which is the title of this session, and then the beyond, the first word of the presentation title, what is beyond that? And I argue that it's empirical privacy risk. Okay, so the foundations of synthetic data and privacy. So there are a couple of paradigms now to generate synthetic data. You could go and like prompt GPT-4 or choose your favorite model and generate some synthetic data describing what you have, or you have some data to start with, right? Like something that is proprietary, something that like contains patient records, or something that is not widely available on the internet for foundation models to be trained on. And you want to generate synthetic data from that. And so in all of these different settings, there's this like a spectrum. In all these different settings, privacy matters. And I'm going to argue that privacy matters for all the different settings based on a lot of research. So there's work that has shown that on the very left-hand side, if you prompt GPT 3.5 with, repeat this word forever, poem, 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 eventually it starts regurgitating like actual information about a real individual. Now, presumably this was part of the training data. And if you actually like look up the person, if you can go to the research paper and like look it up, but you can look up the person and they're a real person, like they exist. They may have a slightly public persona, but they exist. And this might contain information that was not supposed to be public. Okay, so that's one example in the text space. And I'm sure all of us at this point, like use some form of LLMs, even if you just Google, like this can happen. And someone might be sitting there running an adversarial attack trying to get some private data out. This also happens with diffusion models. So a similar set of researchers did work with diffusion models, and they saw that they could extract training data from here. And on the very right side is where you have some data to begin with, and you're trying to train a model such as, I don't know if anyone remembers GANs, but like old school models, or even like Bayesian nets and so on. So kind of like very old style models at this point. Nobody seems to use them, but still, this work on the very right-hand side shows that membership inference attacks can actually be really quite successful on tabular data. And this is data that contains categoric, numeric, and text messages in there as well. So there are a lot of reasons why privacy is important. We can't just say, okay, generative models, there's no like one-to-one association between the training data and what comes out of them. Therefore, we're done with privacy, who cares? No, because there are still clearly risks, and there are risks that we have not identified as well. So really quickly, I argue here in this entire talk that differential privacy is a really good option for us to use to control how much privacy we want in synthetic data. And so natural question is, what is differential privacy? Some of you know what it is, but I'll cover it really quickly. It is a mathematical guarantee that algorithms are designed to meet. And so the guarantee is that if you change the inputs by just a little bit, how much do the outputs change by? And we want to make sure that these outputs change by a really small amount, and we can quantify what that amount is. And that amount is, it's epsilon and delta, like these two Greek alphabets here, these parameterized differential privacy. And at some point maybe you've heard of Apple's deployment, they use an epsilon of 8. Google's deployments use anywhere between 1 and 8, or 1 and 10 actually now. And so there's a wide spectrum, but really academically speaking, an epsilon of under 1 is the thing that differential privacy was developed with. So you can see we've already extended it a little bit further, and now getting to double digits is considered fine. But what is it? It's a ceiling on how much the probability of an output changes when the inputs change. Or an example is added or removed to the data set. So a simple example, let's forget about generative models. If I'm counting the number of people in this room, and I'm looking at a randomized algorithm, so a probabilistic algorithm, I would say, okay, I'm going to roughly count how many people are in this room, or I get an exact count, and then I add some Gaussian noise or Laplacian noise, and then I get an approximate count. And that tells me, okay, maybe there are 30 people here, maybe there are 32, maybe 35, even 40, whatever, that's fine. Or maybe it's actually 20, and that's okay too. But that's the point, that there's some plausible deniability. And delta is the risk that exists no matter what you do with your data set. If you were to publish even a single thing about it, delta is sort of the risk that exists as a result of that. Super oversimplification, but why do I mention this? It's because we use differential privacy, or we use differentially private algorithms. We design them to generate synthetic data. And we provide this mathematical guarantee for generative models. I'm only describing a few things in this slide, and I'm going to go over them very, very quickly. But there are myriad of ways of designing differentially private algorithms. Some folks use GPT-4 also, plus differential privacy to get outputs. But in this paradigm, we're saying you have some private data, right? And private data means lots of records. I'm thinking thousands of records. And you have a generative model. And we're going to apply differential privacy during the training process of that generative model. One way is the simple, okay, we have an optimizer-based sort of learning process, again, a transformer, an LSTM, something really basic that's going to generate data on the other side. And we use something called differentially private stochastic gradient descent, or differentially private ADAM, so you'd add it to the optimizer. So it's changing the training process. Another way of doing that, and so that is applicable to image models, it's applicable to text, tabular, just kind of anything that you can use a transformer for. That's how I like to think of it these days. Another way of doing it is to say, okay, I only have categoric and numeric data, and I'm going to learn a graphical model out of this. So kind of go a little bit old school, but I get a lot more out of my privacy budget there. So that epsilon delta earlier, that's what I'm calling my privacy budget. And I can say maybe for an epsilon of 1, I can really stretch it, because all I'm doing in this lower model is I'm computing marginals and I'm adding noise to count. So think huge contingency tables, and then I just like the count I did here of how many people are in the room. I'm just doing that over and over again for multiple contingency tables. And out comes a differentially private model. And now this thing on the right-hand side, that is the thing that has the guarantee. It's got this epsilon delta guarantee. Everything works as expected. The risk is bounded. This is great. And then it has the property that it has a property called post-processing, which basically means that anything that you do with that model is also differentially private. Okay, so it's a lot of stuff okay, great. Now everyone go home. Your homework is to go and implement this. Just kidding, it's not. You can sort of use differential privacy for generative models using Gretel Safe Synthetics. And this is, we're now part of NVIDIA, but you can access sort of everything through Gretel AI. Go there, get an API key, and it is really simple. So you're writing 10 lines of code and basically saying, okay, for a data set where I have 20,000 input records, I'm going to use a batch size of 32. Then I'm just going to set these privacy parameters, right? Think a YAML file, a dictionary, whatever. I'm just going to set DP is equal to true, epsilon of 1. I'm going for the academic thing of 1. I'm going to set delta to auto, which is just 1 over the size of the data set, or n log n. And I just want to make sure that risk is really small. And I calibrated all of this, and I say, okay, off you go and create this data set, go run a model, create an artifact. Cool. All right, so talk not over. not over, because we have a handful of use cases, or case studies rather, where I'm really going to highlight, like, if you have a data set, either a tabular data set or a text-based data set, and you want to generate a differentially private version of that, how are you going to do that? And what does it mean to be on this privacy utility trade-off, right? Like where do you lie on that? Is it a curve? Is it some sort of idea? Is it something that legal has told you? Is there a policy? The answer is it really depends, but we'll go through a couple of examples. So the first one I have is I took this data set of e-commerce reviews, and I don't know if it's Amazon reviews, it's some e-commerce website. I got it off Kaggle, and I processed it a little bit. There were 23,486 records and 10 columns, and then I did a little bit of curation on the data, and I got the structure that looks like the top left. So there's some reviews, there's the age of the person who wrote it, there's the rating associated with it, the positive feedback count, and just a bunch of other things, right? You could imagine that the name of the person is in here, that there are more sensitive details in this data set as well. Maybe they're text-based, maybe it's like identifying in the way that somebody writes a review. Maybe I'm really verbose when I write reviews, or maybe I'm not, and that could be identifying of me. So I've got this type of data set, and I go through and I like specify all the things with Gretel Safe Synthetics, and I run a model. I created a model. I generated 20K records. Cool. Super simple. This runs for a couple of hours, and out comes a model and an associated data set. I asked for 20,000 records. Cool. But now I set epsilon of 1 and a delta of 1 over n log n. Cool. Maybe that works for me as just someone who's experimenting with this. But what does that mean for you or someone who's using their own data set? Well, you could run this with several different epsilons. And it really depends on like what the downstream use case is. In this case, it is to predict customer sentiment towards a product from all of these different attributes. And what I did very simply was I ran a bunch of models. So from epsilon of 0.1, 0.5, all the way to 10, right? Like the thing that Apple and Google use, or like public deployments of differential privacy use. And I trained models. I generated several synthetic sets. And then using those, I trained classification models. These are just logistic regressions. And I went through and ran a bunch of models. I got some confidence intervals on those results there. And when I'm comparing to the baseline, so the baseline AUC is 0.68. Comparing to the baseline, you can see if I use an academic epsilon of 0.1, yeah, it's kind of bad, right? Like I've lost about 0.1 on that AUC, but that's expected. So that is the trade-off. Like that's what I'm talking about when I say there's a trade-off between privacy and utility. You could do really, really well on privacy, but maybe that data is practically useless, right? Like maybe I could have just prompted GPT-4 and it would have given me something, and it's like kind of not even like my data, but it does the job, and you know, it's over 0.5, call it a day, blah, 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 done. But that model's not going to make it into production. So then let's move to something else. Okay, maybe an epsilon of 5 seems okay because I'm still getting like reasonable utility. Like AUC is roughly within like, you know, 0.01, 0.02, depends on the synthetic sample that I choose. And I can go from there. So it's really a spectrum, and that's great. That's great. So here's an example where I have a mix of text and categoric numeric data. Another example is where I have just text data, and let's say these are patient notes. Okay, so I have an interaction with the doctor. The doctor says, "Hi, Lipika, how are you doing?" "Oh, I'm fine, doctor. I just like, you know, I bruised my knee and then I fell down and I feel like I have something in my IT band, and oh, I really don't want to keep running, but I have to. I have a marathon." La la la. Obviously, that's not the conversation. But then there's going to be some like transcription, and typically, actually, like a medical assistant does this. Like they'll write out what that note is, or like what happened in the interaction as part of training. I think a lot of AI tools are now being used to do that summarization. But the value here is what we're trying to show is that each doctor has a unique way of writing a note. So something that they can quickly scan, you know, like specific details that they're looking for in a specific order, in a specific format, specific like size, shape, whatnot. Maybe someone likes bullets, maybe someone doesn't. And so the idea of this example is that can we generate synthetic patient notes based on an interaction to summarize consultations in a style, structure, and language that is unique to a healthcare provider, so to my doctor. And so we took this data set, like the private data set, we generated a differentially private version of it, and then we fine-tuned Claude 3 Haiku, something that might be used in production in a hospital system, right? To generate something that looks and feels like what the doctor is expecting. And so this is like personalized to a doctor. And what we found was that when comparing this fine-tuned model, which used like differentially private training data, to just what the base model produced, we're able to get like higher semantic similarity and higher structural similarity. And also when evaluating with LLM as a judge, we're seeing that like the style and organization of what's contained in those notes that's summarized by Claude 3 Haiku, like that's all a lot more consistent with what a doctor is expecting. And so that there could be possible utility here. Obviously, these are canned examples, but again, you could do the similar exercise of, okay, I'm going to take an epsilon of 0.1 to 0.1 to 10, and then I'm going to see like how this changes and whatnot, and what kind of guarantee I can get from that. Cool, you could do that, but let's get to the beyond part of this talk in the 4 minutes I have, which is what happens after this. Like, do you actually know, do any of us actually know what epsilon is? Can we measure it mathematically, precisely? Are we going to assign a probability risk definition to every single use case with every single set of neighboring data sets, meaning this entire audience with me and without me? No, that changes depending on the scenario. And it also requires probably someone like me and the rest of my team to figure out, like, this is the nuance, this is the probability risk definition. So what's beyond this? I argue that what's beyond this is empirical privacy risk measurement. And so you would have heard a lot of like attacks on models, right? Membership inference attacks, attribute inference attacks, data extraction attacks. There's a lot that can be done in the model space, but what we do in the data space, so when you have a synthetic data set and you're trying to attack it, it's two different things. One is a membership inference attack, where an adversary basically tries to determine whether a record that is known to them was used to train a model. And we run a bunch of simulations to do this, 360 to be precise. And we also do attribute inference attacks where we say, okay, an adversary knows like some fields in the data set. Can they guess the rest of the fields based on that? So it's a lot of simulation, and it's a lot of like nearest neighbor measurement or similarity measurement type of things that we do. And we get some sort of estimate of what the risk is that's associated with a synthetic data set. And so we're like, okay, great. I generated these data sets with DP, these last two examples, what happens? Okay, so for the e-commerce reviews data set, when I use an epsilon of 5, I get this like membership inference protection score of 9.7, where the majority of records, and I can't read exactly what those percentages are on the slide, but let's say like 85% of the records fall in this excellent category where nothing was able, like an adversary was not able to infer based on the synthetic data set that a real example was in there. But then 15% of the time they were able to do that. So that's for the e-commerce reviews data set. And then similarly for attribute inference protection, for each attribute, you can go through and see like how susceptible is this attribute to being inferred. So that's for the e-commerce reviews data set. For the doctor's notes data set, for a slightly higher epsilon, we get very similar membership inference protection and attribute inference protection. So that's what I argue is beyond just this like privacy utility trade-off. And yeah, that's the talk. There are a lot of ways to measure privacy and utility, and a lot of resources also on how to get started. We've written a lot about these topics. Yeah, open to any questions that folks have.